Alright, so here's a very quick demo of what I've been able to build in 4 months time now. Let's have a look at the GitHub repository. It is now almost 700 commits later, and as you can see, there's 4 months ago and 2 months ago in certain places. So this project has been going on for quite a while, but not long in terms of game engine timeframes. So the first thing I want to very quickly touch on is the scope of the engine, because what I've been building is a game engine with the eventual goal of being able to support virtual reality and augmented reality experiences, because I've been bitten in the ass by Unity, and Unreal Engine is an unwieldy beast. So I decided to make a quick and dirty framework for me to be able to experiment with more low-level APIs, such as the low-level graphics APIs like Metal or Vulkan, and also the operating system, instead of having to rely on abstractions that have been made by an engine like Unity or Unreal Engine. Now, there are very good alternatives to these commercial engines, such as Godot and Bevy, and my personal approach, which is quite common for people developing game engines, is to see it as a side project or as a learning experience instead of as a direct competitor to those. That is what this project is all about learning how a game engine works and also trying to build something, maybe innovate in certain aspects. But mostly what I've been able to build is either getting to feature parity to these open source engines, or being not even remotely close, but it's still being a really good learning experience. I didn't expect to find so many details that just takes so much time. But that was a really good learning experience. Okay, so let's go through the general architecture of the engine in its current state. So what we have is a clear distinction between the application, or in this case the editor, which is a specific type of application, and the modules, which is kind of the core runtime of the engine. And each of these modules interplay with each other. They're not interdependent, it's always one built on top of the other, which makes it modular in some way. And there's only one specific module which multiple might depend on because of certain utility classes. So the first thing to get out of the way is the common module, which contains some very basic things like a logger, an implementation for the observer pattern, and also a way to get value results. It's kind of similar to the C++ implementation for standard expected. However, this is not supported in Clang, which is the compiler I'm currently using. And there's also a wrapper for getting a shared thread pool, or a shared instance of a thread pool. So the goal with the engine was to use as little libraries, as few libraries as possible, and also as few abstractions as possible. So I've also had to write some platform abstractions for the platform I'm currently developing, which is on macOS because I'm using a MacBook. And that is common basically out of the way. Then we have the next important module, which is graphics. And graphics is basically a low-level graphics wrapper, similar to what Meta has created with Meta Eagle, and that stands for Intermediate Graphics Library. And this basically wraps the graphics APIs such as Metal, OpenGL, DirectX, Vulkan, and provides a platform agnostic API without um, without changing the low-level nature of these API calls. So you get all the low-level objects or data structures, such as buffers, command queues, a graphics device, a render pass, a render pipeline states, texture as well, and a window, which is also important because you need to draw to the screen. And then we have certain backends implemented, and the backend I implemented first is the Metal backend because I'm again on macOS, because I'm using a MacBook, and this literally just implements all of the abstract classes that are defined in the graphics wrapper. And there's not that much difference between the wrapper and the backend implementation. There's some detail that gets hidden, but in the end it's quite close. I haven't implemented Vulkan yet, which will be important to support the MetaQuest Pro and the MetaQuest 3. However, that will require some boilerplate, but I will be able to reuse what I wrote an earlier experiment I wrote using Vulkan. So I'll be able to use that. And then of course we have the platform abstractions that interact with the graphics APIs, such as Coca or UIKit. And that's basically to enable the creation of windows. So graphics does contain some extra things than just the graphics wrapper, graphics API wrapper. So it contains input handling as well and window handling. So there's some platform abstractions that might be able to be separated, but for now it is quite closely tied together, especially for window creation, etc. And input is also directly part of a window in macOS, so that kind of messes things up. So therefore we've created a separate module called input, and that basically takes window input, but it could also get input from other devices such as external keyboards or any other thing. So this is something to consider moving forward to refactor or improve in terms of architecture, because we do need to separate input in some way. Then we have an entity component system, and an entity component system is quite simple. It's a data driven architecture, which is similar, or which is different from traditional object-oriented programming methods such as present in Unity with game objects and mono behaviors. And it is incredibly fast because you literally just iterate over a contiguous memory, and you just execute a function over this data, and that is blazingly fast. It just complicates certain things like a hierarchy, so that has been implemented as well. And all of this takes a great amount of inspiration from Skypejack's entity library. The reason I didn't decide to use his library is because it has a lot of decisions made that would influence this code base, and therefore I just decided to take the good parts, reference where I'm using his implementations, and also be able to just strip out to the bare essentials, because there is a lot of complexity that comes with a library that has been actively in development for a couple of years and has also been used in production. So both good and bad things. I wasn't able to comprehend the code that was there because I wasn't as familiar with templates as I am now. But this was important for me to implement myself instead of relying on, again, an abstraction that would make my life easier but harder to moving forward, because I wouldn't understand the way it actually worked. And especially because I need to work with these low-level data structures anyway, might as well just implement them myself. Especially when it's such a core part of what the engine actually is. Another part is the math library. Again, I could have used GOM, but I wanted to know how to implement matrix multiplication and some of the basic types, and GOM also includes certain things that aren't exactly the way I wanted it to be. So again, I decided to take the time to write something that worked exactly for my needs and was also simple enough for me to understand and use. Next to that, there is the ability to specify memory layout. So when you have a type, a matrix type, you can also specify whether you want it to be in column major or row major layout, which is especially important for for supporting different graphics APIs and also different platforms which expect the data layout to be in different forms. So for example, Metal expects it in column major layout, but it's easier to reason about the data structure and the way it gets initialized in row major format. So this enables it to be internally stored as a different memory layout as what gets provided from either disk or from what the programmer specifies. All right, so then we have the next part, that's the renderer, and that is basically the abstractions that are being built on top of the graphics API or the graphics API wrapper, which is in the graphics module. So the renderer has certain abstractions such as a mesh, and a mesh contains different attributes. So there's a lot of different moving parts. That's also one of the learning points by the game engine. It has a giant surface area. So with a traditional application that is not as big as a game engine, you would probably have a lot of business logic and some core parts, but a game engine just has so many different parts, and you just have to make choices about which parts you want to implement yourself and which parts are just outsourced to different different libraries or frameworks or middleware. So this is part of what I want to develop further. I haven't implemented any proper rendering solutions yet, only some very simple things like a mesh and a material which literally just contains a shader which references a shader in the graphics API wrapper. And there is, of course, an ImGUI backend which enables us to render the user interface using our graphics API wrapper and our renderer abstractions. And also the scene currently isn't anything, that's literally just the entity component system entity registry, which contains a set of components, and each of these components has a list of entities which is holding. So those are the scene, renderer, math input, and graphics, an entity, and common as well. So we have a couple left. We have asset left, and we have reflection left, and we have import left. So this is actually the part that I've been working on the last, because, or most recently, because I wasn't able to create this type of stuff before and I had quite a lot of trouble with trying to understand the way that I would be able to implement reflection inside of C++, because it's a crucial part in implementing a game engine, because the game engine needs to serialize and deserialize data it stores in memory to the disk, because otherwise you will lose any changes you make to scenes, or anything you import will be a one-time thing. As well as being able to inspect your data structures in the editor, it's crucial to have some information about what kind of data is being stored in on runtime or on disk. So this is fully implemented in C++. There's no preprocessor magic. It's all just template things. So if you look at the way that classes are represented, is that you have a type info or a class info, and the class info contains properties, and these properties contain nodes, and these nodes are, for example, a list, which is a vector or a dictionary, and this enables the serialization to be done from this description. So you have the node, basically the graph of the type, with the nodes, and that gets serialized to JSON through the JSON serializer, and it literally just takes a type. So if we look at type to JSON, we see that we take a type, which is a standard any, and we put out a JSON object, and that JSON object we can just either read out to a file, or write out to a file, or read in from a file, or any other stream of data. So this is the way that that serialization is being handled. So we have the reflection system, and then serialization is built on top of that. And then we have the asset system, which enables you to asynchronously import and load assets, and also serialize them to disk. So parts of this are not implemented yet, which is the serialization to disk of imported assets, so that they can be loaded more quickly in the future, or on next runs. But what has been implemented is a simple asset database, which enables you to import a file and also get certain artifacts that are being generated by importing a file. And this can be, this is then stored as asset handles, and these asset handles can be stored by simply by an asset handle. So if we look, for example, here into the editor header, we see that we store a mesh, and if we look at where it gets used, we see that asset mesh, or we see mesh.0 equals assets.get, and then we create an asset ID, and an asset ID is comprised of or consists of two parts, which is the input file path and the generated artifact path. And this creates an asset handle, and this asynchronously gets run. It starts a new thread, or it has a thread pool, so it doesn't need to start a new thread every time. But you create an asset handle through this way, and once the asset is imported, the asset handle gets put on green. It's like, hey, I'm done, and then mesh 0 can be used, so it's like successfully loaded. So in a for loop, for example, you would check for the mesh, or you would put it into a separate category, and then if it has become valid, then it would start showing. So for example, you'd create a pool of you would create a tag which is loaded or visible, and then with the observer pattern, once a thread has successfully loaded an asset and the asset handle would be put on green, it would create an event with this observer pattern, and this event would then we would then listen for that event and say like, hey, let's put the let's add the component type or the tag type to the entity component system registry with the name visible or loaded, asset loaded. So that's kind of the architecture that has been set up, and that is quite flexible. Also, asset handles, when you don't keep track of them, they just get destroyed. So if you do import file and later you want to use, you do assets get, it might already in the meantime have destroyed the entire asset handle and thus also the resources it has. So it's important to keep track of the asset handles. So there needs to be as well some way to make sure that import file keeps the file in memory. There's some work to do in terms of management of these resources, especially beyond just simply saying I want this one right now here. But that is relatively trivial to do with the observer pattern. Alright, so here you can see in the editor.cpp that we simply create some objects inside of the registry. So we create an entity, we add some components, also a visible component, which enables it to be rendered, transform component, and you can see that here that we have also introduced the concept of tag types, which enable a system to iterate over which ones it still needs to update, and then removes the tag, and then it never iterates over that again. So if we look at the main rendering loop, then we see yeah, so here we see the function. It's just literally a normal function, not a member function, and we simply iterate over all the types that also contain a transform dirty component. So if there's no transform dirty component, it won't iterate, so it won't have to calculate anything for those. And then we remove the tag, and then we after updating all of the transforms, we iterate again over all the mesh renderers, and then if the mesh renderer the mesh has been loaded, so this is an asset handle thing, then we perform the rendering loop for that specific, or the rendering logic for that specific mesh. And then if we look at the way that the mesh actually gets bound to the buffers for the for the shader, we see that we have a dynamic attributes. So this is something that also needs to be implemented. An asset can have more attributes or less attributes, and we want to compile shader variants for these different attribute types, and we also want to sort them so that we don't have duplicate shaders where the order is different, but there's the same amount and type of attributes. And then if we look at this, it's very simple. We just perform a draw call, and this is of course slow, so you want to have instancing and also batching of similar similar meshes, when they're static, they would have to be combined. So that's a lot of logic that is already in engines such as Unity. But in this engine, there's like no logic at all for that yet. And also one thing that's important is to have a render graph, and that's also not part yet of the engine. So this is a very underdeveloped part of the engine, the rendering, because there's almost no rendering yet. There's been a lot of work on just getting the asset database working, getting some platform abstraction stuff, the observer patterns, getting results, asynchronous stuff in the asset database, of course, having an entity component system architecture, a graphics wrapper, then also the importing I will touch on later, having some input handling that stores like which keys are pressed. Then we have the math, of course, and reflection, which enables us to reason about the data structures inside of the engine, and also visualize them either in the UI or serialize them to disk and serialize them from disk, deserialize them from disk. And then we also have the renderer. So the renderer is underdeveloped, and also the asset database needs some work. And the entity component system also needs to be serialized to disk, which is an important part that is currently not in there yet. So any changes you make are lost forever. So it's very much going to be challenged to go from this outline to actually storing all of these data structures to disk and tying some of these systems together, because you then start to tie together the renderer, the asset database, the entity component system, and also the importing of, for example, a GLTF, which gets converted to a scene, and the scene would be comprised of an entity registry. And so if we are able to serialize the entity registry, we would be able to serialize the scene, and then we need to have the logic in the asset database that actually stores this all into the project load directory. So we have the input directory where the input files are, and the load directory where the cached files are, and also the import results of what has been imported. So that those systems need to be tied together. And also, if you look at the import, I decided to not focus on JSON parsing for loading the GLTF, but just use CGLTF, which is a header only. I don't know if it's header only. Is it header only? Yeah, it appears to be header only. A header only library for importing CGLTF files. Oh no, sorry, GLTF files. And that includes GLB files. So a lot of logic, but or a lot of moving parts. CGLTF doesn't do that much for you. It just literally provides a way to inspect what data has been loaded into memory, and you still have to read out all the data yourself and put it into the engine's abstractions that have been built. So for example, in my case, the way that I built the mesh abstraction, that's a design that I made, and then using this import logic, I need to fill those data structures in, and the CGLTF helps me to not have to parse the JSON myself, and also some additional things like, for example, the interleaving of data and applying sparse data. So there are some things in the GLTF specification which are a bit more complicated than just literally being able to copy and paste the buffer. so you need to take care of that as well. So there are some things that are a bit quicker because I'm using a library there. So right now I wrote a simple camera controller, which is quite fun because that's finally the high level stuff I wanted to work on, which is how does a user actually interact with any of this low level stuff, and what could I actually build with all these low level abstractions. Because if you look at editor.cpp, it's just littered with just some tests, like what kind of assets can I now finally import using this new asset system. And then you start to realize, like, okay, there needs to be a lot more than what has been created, because there's still manual labor. You wouldn't want to do this when you're working on a project. But overall, I'm quite happy with what I've been able to achieve in in just 4 months. It's like about 180 files, and if we look at the code base, it's still quite small. I also don't try to write as much code as possible. I try to be as expressive as possible and as terse as possible, while still maintaining readability. It's about 180 files, so still a relatively small code base, but there's a lot of moving parts, and I expect the size of the code base to not grow that much more. Like, if I implement all of the things that I just described, it will probably be around 20,000 lines, and we'll have the serialization of an entity registry and just some stuff like storing the imported assets into the load directory. So overall, quite happy about the architecture and the decisions that I've made so far. It's not tightly coupled. There's the abstractions that have been written are somewhat okay. And C++ overall hasn't bitten me in the ass as much as I had expected it to. There's of course some troublesome things, but I've been able to avoid that by keeping things simple, relatively simple. So moment of truth. Also for PNG, I use load PNG, which is an alternative for libpng, which is faster. And yeah, so we have the thread pool, load PNG, JSON parsing by, what's it called again? And Lowman formatting, because in Clang standard format doesn't work yet. Date, I don't think I've actually used that, and CGLTF. So very little external dependencies. ImGUI, of course, which is the classic in game engines. Very little dependencies, keeping it nice and clean, while still providing the type of engine abstractions that you would want in an engine. And if we start the editor now, this is the moment of truth. Here you can see the editor and also just the sheer lack of anything or any features. I've been able to get the input working with ImGUI, and I can type in things. So let's say we want to change the scale of entity 1, we can do that. And you can see here that there's still some stuff about IME stuff, which is complicated stuff. That's input handling for different languages, etc. So yeah, it's just ImGUI. ImGUI is very, very nice. initially I was like, oh, I wanted to make my own UI framework, but that's a bit unrealistic at this moment, so I'll just use ImGUI as a starting point, and then focus on the rendering and the logic first, and then afterwards start with some sort of UI framework. But there's no point in reinventing every wheel possible. So here we can see the simple camera controller. It's literally just first person WASD, which also required some quaternion and matrix multiplication and vector math. And here you can see two different GLTF files which have been imported with assets that are textured using imported textures. So very simple stuff, nothing too complicated. But it does rely on a lot of these low-level abstractions and implementations. Here you can see a shader that I wrote, which doesn't take the position arguments and the camera position into its buffer, but literally just draws it onto the screen. So yeah, traditional graphics programming techniques are still present here. And of course, the most beautiful part of ImGUI as well is the let's see, style editor, colors. I really like the color picker because it makes it seem like this is a creative application, which it definitely isn't yet, but I want it to be. So that's kind of where I am right now here. And if we go over here, we can see that there is a separate, what's it called? GLTF file. This was imported from GLB, and the one that I just disabled with the island, that is a the scale was off. Which one was it? 1. This one is a GLTF, and the difference is that GLB contains all of the buffers for the meshes and the textures inside, or not textures, because they can be embedded, but they're not in this case. They're separate. And the GLB or the GLTF is literally just a JSON file that references the buffers or external buffers. So yeah, a lot of work, a lot of progress, a lot of stuff that still needs to be done, and great learning experience. I think I've covered everything I could have potentially covered. And thank you for watching this video. And I'll see you in the next time, where I will finally not have to look at this island again. So one thing you can see is that there's some flickering going on, and I need to figure out whether that is something to do with the Z buffer being incorrectly specified, or that this is something that's wrong with the mesh. Right. Thank you. Bye-bye.